All right. Manish, you just beat me to it. I was just about to turn that on. Okay. So today we're going to start talking about ordinary least squares or linear regressions, or sometimes they're called linear models. Um, there's a lot to cover in this topic, and it's going to take more than 1 week. So I have a lot of material to cover today. My plan is to hopefully get through it all, but on some of the more complicated details, sort of just try and get you through the 10,000 foot view. And next week we'll go back and we'll do more details and more examples. And by the end of next week, hopefully we'll, not able to hear you. Let's see. Okay, according to my screen, I am making noise. And so the person who said they can't hear me, I suspect the problem's at your end. I seem to have everyone else saying they can hear me. Okay, so, but just to repeat, we're going to start with regressions and least squares. And this will be 2 weeks worth of work. So let me just start off by saying, what do we mean by least squares or linear regression or ordinary least squares? All these terms are informally at least used interchangeably. And so there's a mathematical aspect. I don't know why some people are having problems with the audio. Most people are not, so it's not at my end. You need to check your settings. I've had a bunch of people say they can hear me.
I think only Ajay is having problem. I don't think anyone else. Can you please raise your hand if you're having problem hearing, if it's not audible? I think it's only Ajay who's having problem. Can you
Right,
review? Ajay, can you restart or rejoin?
right. That's the only thing I can suggest. If there's only one person having a problem, there's nothing I can do with it on my end. Shall we wait just a minute and see if he can rejoin with and here? All right, so I'll just continue with the introduction. So least squares has a mathematical and a statistical aspect to it, and it's good to understand which is which and what you can do. So the math is a linear representation of your data, and by that I mean you have some data and you want to create a model, which is a function, so that you can represent your output as a function of your input. And that's a math question, and it can always be done. But the statistics question is, how good a job does this representation do? I mean, is it reliable? I mean, when you say, your y variable is 3 times your x variable, is that 3, likely to be right? I mean, what's the range of your estimate? If you did it again, are you likely to get 2.8, or are you just as likely to get 7? So sort of what's the 95% confidence interval for your estimation? And that's the statistical aspect, but we need to understand both. So the goal for this talk is I want to explain least squares. I want to explain the statistics involved. I want to explain, what a linear model is and when it's appropriate, how you can use R to create these linear models, and this is, critical. What is the output of the R function? Because it really gives you a lot more than just here's an equation. Some troubleshooting and generalizations. And of course, not on here, but true as examples. And the last two are going to be mostly for next week, but there'll be some talk about that, particularly troubleshooting. Okay, so the mathematics of least squares is as follows. You have a bunch of data points. For example, you may want to explain the amount of rain in terms of humidity and barometric pressure. You may want to explain one stock price in terms of another. You may want to explain somebody's income as a function of how much schooling they've had. So in all these cases, you have a dependent variable, the y, which is what you want to explain, and an independent variable, x, that you want to use to explain it. And so you want to get a model, and a model simply means an explanation of how these items are related. And so the simplest model would be a linear model, because linear functions are the simplest functions that exist. So in case we're unclear, what I mean by linear, I mean we can write y equals ax plus b, and a and b are just real numbers. So that means if I want to know what my value of y is, I have my known value of x, I multiply it by a and add by b. So here's some examples. Y equals 3x plus 2. Y equals, excuse me a second, I want to write something. I apologize, this didn't come out quite right. Y equals negative 5x plus 7. These should be on separate lines. Or y equals 11.63 to the 8th power minus some really humongous number. But the point is in all these cases, if you give me an x, I can always tell you what the y value is. It's very simple to compute. And incidentally, one of the things about linear things is anything you want to do with linear things can be implemented in a computer, always. And to go back, it says a is the slope and b is the y-intercept. So we have y equals ax plus b. A is the slope, and this is how much on average, it's saying basically how much y will change if x changes by a given amount. And b is the intercept of the y-intercept, because when you said x equal to 0, if you said x equal to 0, what's the value of y? It's b. A times 0 plus b is b. So b is the y-intercept, because that'll be a point on the line. Okay, quiz 0 is, I have this equation, y equals negative 6x plus 2. Which of the following is correct? The slope is 2, the intercept is minus 6. When x equals 0, y equals minus 6. When x equals 0, y equals 2, so 2 is the intercept. I will, so this is really just, this week I figured out how to do this right. So let me go to polls. Okay, so there now you should see a poll is open. So you can answer one of these 4 questions, one of these 4 answers, 1 through 4. All right. This seems to be unanimous. I'll give you just another 10 seconds for those of you who feel like it. Okay. All right. No, everyone who did vote voted for number 4, which is correct. When x equals 0, y is minus 6 times 0 plus 2. So y equals 2. When x equals 0, y equals 2, and that means that y is the intercept. When x equals 0, y equals 2, so 3 can't be right. Again, this means the intercept is 9, not minus 6, and the slope is 2. The intercept is 2. The slope is actually minus 6. All right. So I've created a data set called my data, and it's a data frame as it is. And here's just a simple graph of it. So this is all the data, and this I just used making a simple plot. So I just hit plot of my data, and this is what you get. And if you were trying to look at this data, you would say, well, clearly this data doesn't lie in a line, but you can see a distinct trend. And so what you could easily believe is that the data represents some sort of linear trend plus noise. And so you could believe that there's some line that's going to describe the data pretty well. So if we look at it, for example, we can see that the data is highly correlated. Of course, x and 100% correlated with x, but the correlation of x and y is 0.86. But going back, a question you might want to ask is, say, all right, what's the slope of this line? I mean, and now it's a little bit deceptive because x runs from, in fact, -5 to +5, and y runs from, well, it looks like about -20 to almost 30. So the scale, so it doesn't look like the slope is very big, but this is a function of the scale. So we have that information. We took a look at it. So quiz number 1, and this is just a participation quiz. Given what I've just said, what do you think the slope of this line really is? So this is just asking you to this is really just asking you to just make your best guess. There is no right or wrong exact answer. So the 4 choices are about 1, about 3, about 0.86, and about -1. I'm going to see what's coming in here. I have about 1 and about 0.86 are the only 2 answers so far. Everyone should do it. There's no, I don't know who answers what, and you know, I don't care. Can I re-show the graph? I had a question. That's a good thing. This is the graph, and you know, it looks, you know, so it's sloping like that, but it's important to keep in mind this goes from -5 to 5, whereas this looks like it's going from about -20 to 25. So in other words, the y values are exaggerated relative to the x values. And the 3 choices, as I said, are about 0.86 and about, about 1, about 3, about 0.86, and about -1. The screen is still on quiz 1. This is quiz 1. The first quiz, so somebody said they're only seeing quiz 1. This is quiz 1. The first quiz was labeled quiz 0.
Hey,
Yep.
Adam, Lauren is saying that she cannot see the graph again because quiz 1 is in progress, so your screen is not visible to her.
Oh, I'm sorry. I misread her question. I can't show the screen anymore, unfortunately, until I close the quiz. So I'm sorry, Lauren, but I can't show the quiz again. That's just an undocumented feature of GoTo training. Poll must be closed to enable share screening. But I remind you that it showed a gently uphill, but the y's go from -25 to 25, and the x's go from -5 to 5.
And I think that the choices were A was 1, B was what was it?
Okay,
Can you
I can
repeat
tell the
that?
choices, Manish. I have them in front of me. I can see my screen. So
Yeah.
choice 1 was about 1. Choice 2 was about 3. Choice 3 was about 0.86, and choice 4 was about -1. Okay, so those are the 4 choices. So I'm going to close the poll so I can discuss this. Okay, so the results were 29% said A, about 1. Nobody said B, about 3. 57% said C, about 0.86. And 14% said D, about -1. Now, I have to be honest with you, and my answer was A, about 1. Now, what I can say is about 1 and about 3 are the only 2 reasonable choices. About 0.86 is not going to work. 0.86 is the correlation. Correlation measures the angle between 2 lines. So regardless of what the slopes of the lines are, you're just going to get a number between -1 and 1. So for example, if I had one line whose slope was 1,000,000 and another line whose slope was 1,000,001, those two, thought of those as data, the correlation of those 2 data points would be almost 1, yet that has nothing to do with the slope. About -1 can't be right, because that would mean the slope was negative, and clearly as x was going up, y was going up. So the only 2 choices that are realistic actually are about 1 and about 3. And I looked at it and scanned and said, yeah, about 1 is right. Now, due to the abilities of R, we can actually just check that. So, as I say here, eyeballing the data, number 1 isn't a bad answer. The slope doesn't look like 3 to me. Correlation ranges between -1 and 1, so the slope is not connected to correlation. And as x goes up, so does y, so the slope can't be negative. And the answer is we can find this, and let's not worry, for example, about what this means, but this, just take my word for it for now, that what this does is this will give me the slope and the intercept of the line. And it says the intercept is 2.8 and the slope is 2.8 also about. So the correct answer was the one that no one, including me, guessed when I just did the thing eyeballing it, and that was 2.8. And I kept it this way, and I didn't pretend I guessed right, because there's an important cautionary message in that, which is that graphs can be very helpful, but they also can be deceptive. In this case, the reason why we all thought 1 instead of 3 was because the difference between the x-axis and the y-axis, the scales of the x-axis and the y-axis. But in fact, the right answer is it has intercept about 2.8 and slope around 2.8. I'm just going to do some graphs on this. We haven't really done too much, except I've sort of explained that, if you have some data, and there are times when you can, look at it and say it really looks like you can explain it with a simple linear model plus noise, and I've given an example to show how that works. And so are there any questions so far? All right.
Adam, I have one
Yeah.
comment.
Yeah.
One way to probably guess the intercept slope could have been because you were saying that the y-axis is going from -25 to +25, and the data was spread from -25 to +25, and x was ranging from -5 to +5, and the function was y equal to ax plus b. So probably, if it was linear, then for each run of each increment of x, the scale was at least 3 to 5 times bigger. So one way, but again, you cannot guess it right, but one way of estimating.
So what Manish is saying is that you might have guessed 3 because the scales is deceptive, but I made the data, so I certainly knew what the answer was. I, along with everyone else, was fooled by my eyes. So it's a good cautionary tale. But Manish is absolutely right. If you had paid attention to my hint that the y scale was a huge multiple of the x scale, you would say, even though it looks like it's about 1 to 1, that means y is going up a lot more, because each sort of distance change in y is in fact a much bigger difference. Okay, so I just want to do a little bit better graphing. We've spent some time on ggplot, and when you start actually doing this stuff for a living or for fun and profit or fun, or whatever, ggplot is going to be really helpful. And so it makes complicated graphing much simpler to do. The bottom line is it makes simple graphs complicated too. So if you just want to quickly see something, don't be afraid to use plot or hist, which are the basic R functions for plotting data or getting a histogram if you just want to take a quick look. But if you want to do better stuff, you should use ggplot. So this is a plot of the data in just a little bit nicer. And again, as Manish said, and I had pointed out, if you look at the scale of the data, with y going from, it looks like 30 to -15, but x only going from -5 to 5, you see that y is really increasing more. And how do I do this? I just want to say, ggplot, and I gave it the data, and I told you the data is my data. Now aesthetics, it definitely is always going to include what you want the x and y is. So I've just said all these plots are going to have this data. The data is my data, and x is the x value, and y is the y value. And then I made it, I said I want to plot, a scatter plot, which in ggplot is geom_point. And I said make it red. And then I put a title, just the data. Now here I've done something slightly different. if you were interested in sort of seeing how things look, the geom underscore line uh, says you draw a line between all the points, and that's what it's done. And I've also, the actual data points we have, I put those in. And remember, with one of the really nice things about ggplot is it's just so easy to add more than one kind of graph. And so here, really, what I've done is I've added the point and the line graph together. Now, in this case, it's kind of screwy, but you see even better sort of this issue. And remember, it's very important to add the plus, otherwise it doesn't know what it's doing. So I've said, here's my basic data. I want the x to be the x and the y to be my data y, and make a line of blue, and make the actual points I have color red. Okay. Then finally, the last one I want to show you is, if you wanted to get it, geom underscore smooth, remember, that gives you sort of its best estimate. So if you look at it, this line is not quite straight, but it's showing you that there's a huge linear component to the data. And remember, with geom underscore smooth, and I've said do it in green, it not only gives you the actual data point, but it gives you sort of a confidence interval for sort of, what it thinks it could be with noise. So we can see there's a lot of noise in this data, but you can see the clear underlying trend with this, and you can see that it looks pretty much linear. So that's how you could use ggplot to take a look at the data. And one further point, if you know you're going to do the same thing every time, like you're always going to have data as my data and with this aesthetics, or let's say you always know you want, this is your data and this is your aesthetics, and you always want the points there with the color red, you can encapsulate it. So if I have P equals ggplot, and then I have P1 is, the same ggplot plus gm, I can look at these different things. So the first one is just P1, so this is showing that, and the other one is P plus, and I've added that. So if I knew I always wanted my data to be this, and sometimes I wanted to add the points and sometimes I didn't, I just hit P. So you can see this is P1, and this is P, and they are identical. That's the point. Is so if you have a long complicated expression, you can just sort of say, I'm going to call the expression this, and then just do that. So if I add P plus geom point color equals red, that produces this. Okay. Now what's the best line? Well, here I've done it. I know I want my ggplot, I want my data, and I want my geometric point, the color equals red, that's P1. So I want P1, and then geom underscore smooth. Remember, that showed us the best sort of thing, but if I say method equals LM for linear model, it's going to just produce the best line, the line that best approximates the data. All right, and there it is. Now notice when x goes from -5 to 5, so thing of 10, this roughly goes from -10 to +18, so a difference of 28. So we can see a slope of 2.8 was in fact about right. And I point out to you this SE equals false. Now what does that mean? Well, SE stands for standard error, and it means just show the line, don't show the sort of confidence interval you have. However, if I say SE equals true, we can see what the one standard deviation, one standard error confidence interval. And by the way, one thing this points out is this data is very noisy, because a significant portion of the data points lie outside the estimate. So what this would say in the real world is already you could see that this model is really, this linear model is in capturing the gist of what's going on, but this, due to a lot of noise, it's not going to give you very good estimates of your actual data. Okay, so this is just going to be a true or false, and in case this is unclear, let me just say it. So the question is asking the command p equals ggplot. So you let p equal ggplot of my data, and I tell it what the aesthetics are. And so I want to say, if I say p plus geometric point, that's identical. It gives the same output as if instead of writing p plus geometric point, I just use the ggplot equals data stuff and that. So I'm going to actually create a quiz. So Remember, true would mean that P plus a geometric underscore point is the same thing as writing out what P is, okay? So think that, and then we'll go to poles. There's two. Launch. Okay, I have to be honest with you. I think I pretty much have given it away, so everyone, and the audience seems to be agreeing with me, since everyone is voting true. All right, so I'm going to give you 5 seconds in case you want to vote, and then I'm going to close the poll. All right, so it is true. I just want to, it is true. I mean, that's the whole point, is it's just an abbreviation. If P equals ggplot, P plus geometric point is whatever P was plus geometric point. Okay, so just one final plot. I won't spend a lot of time on this. I've just added another line, geoms or underscore line, intercept equals 2, slope equals 3, and black. So this is actually, this line is the actual data before I added the noise. So you can see how the linear model, because of the noise I added to it, was unable to capture the true value. But this is it. And you get an idea, I think, of how you can produce very interesting and reasonably complicated graphs without too much work. Once you've gone to the basic trouble of doing the basic ggplot, you just keep adding things and it just keeps showing up, and it's very nice. Okay, so what is the true line and the LM line? So as I said, I created the data. First I set a seed. Whenever you're going to be using random variables, you should always set seed. This means that whenever you do this, at least on your machine, it'll produce the same answers. So I set seed. I said x equals sequence from -5 to 5, bi equals 0.1. So I just created, a sequence of 101 numbers from -5 to 5. And then I said y is 3x plus 2. That's the deterministic equation. That's why I said the slope should be 3. And then I always say run if, but it stands for r uniform, and then r norm. So r unif 101 minus 2, 2, and r norm 101, 0, 5. And just if I wanted the actual data, is equals 3x plus 2. And then I just create a data frame. My data is data frame. I said x equals x and y equals y. That means I'm going to have the two variables are going to be named x and y. Now, R uniformly picks out numbers. So 101 means I want to pick out 101 numbers, and from the interval -2, 2. So pick 101 numbers uniformly distributed from the interval -2 to 2. So that's what uniform noise is. It means, you're just as likely to get any value as another. Now with a normal distribution, of course, that's not true at all. You're way more likely to get a value close to the mean. So then I said, take a normal distribution, pick 101 choices of a distribution with mean 0 and standard deviation 5. Remember, with a normal distribution, 95% of your data is within 1.96 standard deviations of the mean. That's not true with uniform. Okay, so R normal gives normal noise, so it gives 101 observations of a normal distribution with mean 0 and standard deviation 5. And the uniform just randomly picks from the interval. Okay, so this is a true and false. If I take R uniform 101, 0, 1, so that means if I uniformly pick 101 numbers from the interval 0, 1, that'll be the same as taking a normal distribution of 101 numbers with mean 0 and standard deviation 1. That is, both commands will produce 101 observations of random noise with mean 0 and standard deviation 1. And it's true or false. And again, I think based on my previous discussion, this should be a reasonably easy one to answer. So I want to go to Somehow quiz 3 didn't make it on here. Okay, so in this case, answer just by, polling me, by, chatting with me. So the question is, and now, Lauren, you can definitely see the question. Right, so basically saying, well, our uniform 10101 produce approximately the same output as our normal 10101. And that's the question. So I have 2 for true. Okay. And I have a couple of falses, which makes me a lot happy, a bunch of falses, because the answer is false. As I'm at pains to point out, this is going to give you 101 numbers uniformly distributed in the interval 0, 1. In particular, there'll be no negative numbers, whereas our norm 101, 0, 1 will give you 101 numbers with mean 0 and standard deviation 1, but you would expect approximately half of those numbers to be negative. Now, just to echo a previous lecture where we did this, we can check this by drawing the graph. So I can say x is sequenced from -5 to 5 by equals 0.1, and y1 is the density distribution for a normal distribution with mean 0 and standard deviation 1, and y2 is the density for a uniform distribution that runs in the interval from 0, 1. So if we look, this is the normal distribution, and as we could tell, that's the bell-shaped curve. And as I said, in particular, half the answers are less than 0. Whereas this is the uniform distribution, and look what it shows. Between 0 and 1, things are uniformly distributed. It doesn't have any. There's 0 chance it'll be outside that interval. So they're very, very different. So our produces uniform errors, which are very, very different from normal distributed errors. So if you want to make give your model noise that linear model will have issue with, you can use R uniform. Okay, so we've spent some time basically thinking about what the best line approximation is, and I want to just spend a little bit of time making it more mathematically exact, because that will be useful at some point later on. So I've said many times the phrase, the line that best captures your data. So,
Hey, Adam,
yeah.
just one. I just want to make sure that people understood this last point, because a lot of people said yes between uniform and normal distribution. Just want to make sure that they got your point, that uniform is so different from normal.
Repeat it. So the point is that the uniform distribution is incredibly different from the normal distribution. Here's a graph of a normal distribution. When you have a normal distribution, you're always most likely to get values very close to whatever the mean is, in this case 0. And it tails off rather quickly, so as you can see from this, most of the data was within 2 standard deviations. Compare this with a uniform distribution. This says that every value in the realm, now in this case our uniform distribution was on 0, 1, so it says you're equally likely to get any value in that range. Okay? You're just as likely to pick 0.2 as you are to pick 0.8, as you are to pick 0, as you are to pick 1. Now, what's the probability you're going to pick -4? 0. What's the probability you're going to pick +4? 0, because you just take a uniform distribution on the interval 0, 1. On the other hand, from this, it's clear that while you're not very likely to get an answer around 4 or -4, you will get an answer around 4. So and I guess if you want me to amplify, the one thing I'd point out is that when you have a normal distribution, the 0 and 1 is the mean and the standard deviation of the distribution. If you have a uniform distribution, okay, the 0 and 1 means something very different. It's just the lower limit and the upper limit, right? Okay, so if we have data points x1, y1 through xn, yn, we could plot them, and we did, and we want a line that's closest to the data. So at the ith point, there's two things you can say. We have yi, which we actually have the observations, and if we were using the line ax plus b, we have axi plus b, which, if you will, is predicted. And the difference between the two, sort of a measure of at that point how close our approximation is yi minus axi minus b quantity squared. Now, why do I square it? I square it because if you don't square it, some of these could be negative, some of these could be positive, and the differences could be zero. So if I have a line, for which some of these are really large and positive, and then you have some that are really large and negative, if you don't square it, it's going to look like you have a very good answer when you sum them all up. So you need the square to deal with negatives. And then what you want to minimize is the sum over all your data points of the errors, if you will, at each of the points. Okay? Now, it's not a class in mathematics. Let me just think. So L, I'm using to stand for loss. It's a loss or an error function. If you think about it, this L of AB is how much your model is differing from what you're observing. So so when it's saying how much you're going to lose or what your error is when you use AX plus B instead of your observations. So a different net, that's a nice one. So the different, and the thing is it's absolutely standard in this context to use this loss function. But if you use different loss functions, you would get different estimates. And there are times when later on in this class sequence when you'll want to look at different loss functions when we get to machine learning. Okay, but the miracle of modern mathematics. This is solved. B is always the mean of the data points y, that is, B is the mean of y, and A is solved by this sort of complicated looking thing. You take the sum of the xi's times the yi's and divide by the sum of the xi squared. Okay, and as we'll see in a minute, you don't have to do any of this work. R does it for you with the LM function. And make a couple points. This is not so new. This is, gosh, let's see, I think this was discovered around 1800 by Gauss, and he was examining errors in astronomical observations. And what he discovered was that not only was this the method to sort of get the best estimate of what he was doing, but he discovered, at least in that case, that his error terms, the difference between his estimate he got by plugging in this A and this B, and what he was actually observing was normally distributed. And that is how he discovered normal distributions, which is why they're called Gaussian distributions sometimes. Okay, but bottom line, this can be solved pretty easily. And in fact, the constant term will just be the mean of the data, and this A is given by this formula. I'm sorry I couldn't get this bigger, but the point is that I like this graph because it shows you exactly what's going on. The dark brown values are what you observe, and what you predict are the dots, the white dots on the line. And the error terms are the length of these lines between what you observe and what you predict. So for example, looking at this data, in this case, the prediction was really good. This case, the prediction was really good. This one was not so good. And in this case, you can see the prediction was as bad as any of them. The distance from there to there is quite large. But that's what the least square is doing. So for any line, you get a bunch of these white lines, and you can add them up. And what the mathematics tells you is if you use those values of A and B, that'll minimize the sum of these distances, that how much overall your data differs from your estimates. Okay, this is probably a good time for me to use the magic words. Any questions? So I've opened up chat. Okay, so I mean, this is not a math class. There will be no proofs. There will be no quizzes on the math per se. But do we get the idea that the least squares line as a mathematical object is finding the line that best fits your data? That's the key takeaway. All right. And I'm going to move on. So we can find all this with using R, and the function is called LM for linear model. And remember, I just had my data y and x, and I wanted to predict it, so I just call model.1 LM of y dot x. And the reason to do that, okay, so I'm asked that if you don't have a computer, how do you find the best line? And the answer is very slowly. And I mean that kind of as a joke, but I also don't mean it as a joke, because in the old days, calculating these things were very, very hard. So in some sense, solving this problem amounts to solving a bunch of linear equations in unknowns. So in this case, I had 101 data points, and so morally it would amount to calculating the solution of equations of 101 equations and 101 unknowns. Now, in the 1950s, a man named Vasily Kondratiev won a Nobel Prize because he created the first econometric model of economy. And writing about it, he said we had this huge number of variables, but we knew we couldn't do it on our computers, so to bring it down to a realistic time, we reduced it to, I think it was 40 variables, and that took a computer 3 days to run and produce our first model with actual numbers. Nowadays, with modern computers, we can do literally hundreds of thousands, millions of variables, a million equations and a million unknowns in way under a second. So the answer is, in the absence of a computer, a lot of this stuff is somewhere between very hard and impossible to do. And that's, by the way, an important point that's worth keeping in mind, not just for this, but in general about statistics. In the old days, statistics was meant to deal with statistics that didn't have a lot of data, because if you had a lot of data, there was nothing you could do with it. I mean, in 1900, if you had 1 million data points and you wanted to calculate the mean, it could take weeks. It could take weeks for people to, do it and double check it and triple check it and make sure it's correct. Now it's a split second. So the kind of things you can do, the kind of ideas you can use is very different. So in the absence of computers, we're not having this class, not just because this whole thing is being done on the web over a computer, but because doing these things is just too cumbersome. But we do have computers. And with my computer, I say LM, Y, and then tilde sign X. And I create an object. This is a function LM. And usually you want to save the output. And then I just did summary. And let's go over this. So when I ask for the summary of it, it says the call is LM, formula equals Y comma X. Now formula is in fact an R construction. Formulas are kinds of lists that have very specific things. If you tell R something is a formula, it knows that it wants to compute the left side as everything to the right of this tilde. Okay? Next, it has residuals. Residuals is telling you, the residuals are the error terms. So this is important. Residuals are error terms. They mean the same thing. So this is telling you how much your estimates that you got from this model differ from the actual values. So it's saying basically half of them were greater than 0, half of them were less than 0. The worst was off by about almost 15 on the low side, and again, 14 on the upside. But 75% of the data, you were within between -3 and plus 3.5. Okay? Remember, the first quartile means the data that's 25% is less than it, and the third quartile means 25% is greater than it. So between the first and the third quartile, you have 50% of the data. So 50% of the time, the errors were between -3 and 3.5. There's the coefficients next. Okay, you have the x, the intercept, and the x. Okay, so the x is the coefficient of x, and you can see it shows you 2.8 and 2.8. Standard error, t-value, and the probability of greater than t are very important pieces of information that need to be understood properly. So what this is saying is under the, and I want to say this without having said exactly what these are yet, but there are certain statistical assumptions that need to be made about the error terms. But under those assumptions, It's saying the standard error here is about 0.5, and the standard error here is about 0.16. What does that mean? Remember, you're assuming that you're seeing real data plus noise. And under the statistical assumptions of the noise, which basically is that they're normal, and I will talk a lot more about that, don't you worry. But under that assumption, it says if you repeated it, if you drew again the same data, same noise, you wouldn't get exact same answers, but you'd expect the one standard deviation to be about 0.48. So in other words, what this means is you'd expect about 95% of the time you were going to get an intercept that was 2.8 plus or minus 2 times this, 1.96 times this. Okay. Similarly, notice the standard error for the slope is much smaller. So it's saying that you have a much better estimate. Hold on a second. It's asking me to close something. Okay. It's asking me to close things. I have nothing I can close. No, that wasn't it. I don't know why we're having internet difficulties. I stop me if you can't hear me. Okay. So anyway, notice it's saying that the estimate for the slope is much tighter. Okay, it's about a third. So in other words, it says 95% of the time you're going to get an answer of about I'm rounding off 2.8 plus or minus 0.3. Now the t-value is a normalized value. So in fact, the t-value is your estimate divided by the standard error. Okay. And in fact, if you took 2.8 and divided it by 0.48, you would get 5.74. And if you took 2.8306 and divided by 0.1677, you get this. Now, this PR, sine absolute t, what that is saying is the probability that you would get a t-value that great under the t distribution. If under the hypothesis that the true value is t. So this is a measure of how likely it is that your coefficient is actually 0. So it's saying there's essentially, well, it's saying in this case it's 10 to the minus 7. In this case it's smaller than the smallest number that R has, that these coefficients are actually 0. So this is sometimes known as significance. So these are suggesting not that the true values are 2.8, but all this is saying with really high probability, and again, under the assumptions about the distribution of errors that we will talk about, the probability is really high that in fact these coefficients are non-zero. So in other words, what this is saying is that it's really highly probable that X and Y are related. And then the significance code just tells you what these mean. Now the residual standard error, we won't spend a lot of time. This is, you have the errors. This is the standard deviation. So on average, it says by that. Multiple R squared and adjusted R squared, they're almost identical in this case. These are measures of sort of how well the data fits your estimated data fits the model. Now, everyone, R squared is something we're going to talk about. Adjusted R squared comes from the fact that it was discovered that when you had a lot of variables, we only have one in this case, but when you have a lot of variables, R squared tends to be inflated. It really overestimates how well you're fitting the data because you just add more variables. And I'll explain that a little bit better later. But the point of it is whenever you add more variables, R squared always goes up, regardless of whether you're adding anything of value to your model. So adjusted R squared is a kludge, if you will, that attempts to take into account how many variables you have and lowers the R squared, based on having more variables. In this case, there's only one variable. They're essentially the same. And the F statistic, p-value, again, this is not very relevant for one variable model, but it's the probability that all the variables in your model are actually 0. So it's basically the probability that your model is useless. And I'm saying there's basically no chance. We've really done that. And the one thing that's a very sort of weird feature of R is if you just want to know the R squared, this is what you have to do. It's one of, so we have this object, model 1, and it's not part of the model 1. If you take summary of model 1, that's a different object, and in the summary of model 1, it has one of that object's features is R dot squared, and that gives you the value. And so if you just need to know what the R squared of your model is, for example, if you want to plug it in somewhere else in other code, this is how you call it. Summary of model of your model, $ R dot squared. Okay? And if you just want the coefficients, excuse me, this is just something in model 1, COEF for coef or for coefficient will give you the coefficient. So if I just say coef model 1 here, it gives me the X and Y value. All right, so this is a pretty big mouthful. Let me pause and say, are there any questions on this? Is there any part of this you want me to go over again? Or is this all reasonably clear? So does anyone have any questions about any of this? You create the model by using the LM function. The formula you give it is, in this case, since y, you want to predict y in terms of x, y tilde x. And the summary function on the model gives me all the basic information. If you want to, on the t-value, so I'm asked if I can explaining how we get the t-value. So as I said, the t-value just comes from dividing your estimate by the standard error. Now, this is not a normal distribution, but under the assumptions, under the correct assumptions of the distribution, under the assumptions on the distribution of your error terms, the estimates you're getting will be a t-distribution, and with mean zero. You know, your hypothesis is that your true value of the intercept and the true value of your slope are 0. And under those assumptions of the normality of the error terms, this estimate divided by the standard error is the t-value. Of course, there's going to be essentially, once you have enough data points, there's going to be essentially the p-value. So, I mean, which is going to be essentially, the distribution is going to be essentially normal. So it's, instead of a t-value, it's a z-value. But so it's saying that, if you will, it's like saying that the z-score is 5.744. So in other words, if the true value of the intercept was 0, then the z-score of the value you got would be 5.74. What's the probability of getting a value of 5.744 or higher on as a z-score or a t-score? It's 1.02 to the -7. Similarly, you have this estimate, and you get this t-value that's really huge, and it's under the hypothesis that the slope is actually 0. What's the probability of getting a t-value of 16.881 or larger? It's essentially 0. So these standard errors can be used to get t-values, and these probabilities are the probability that given what the data you observe, that your coefficients are actually 0. It is not saying you that the probability is essentially 1, that the true value is 2.8. It's, if anything, it's saying that with 95% confidence, you can say that the true value of the intercept is 2.8 plus or minus 1.96 standard deviations times 0.49. Okay, so, and the question is how can you tell if X and Y are unrelated? The answer is, and I do have an example of this later on, is if I had X and Y were noise, you would expect to see that these probabilities of getting these things are very large. Maybe we can do a simple example in R. Okay, so Control L. Let me maximize the screen. Say AA, oops, excuse me, equals R norm. Okay, so somebody has their microphone unmuted. I thought I muted everyone. I'm sorry. Give me half a second. Okay, it seems to be good now. And I'm going to let BB. Okay, so I've created two variables, AA and BB, which are just random noise. So there should be no relationship to this. And now if I let, I'm just going to call it ma equal linear model, BB colon AA. Okay, oops. This will work better if I use the right nomenclature, LM. Okay, so now I've created a model where I've modeled BB in terms of AA. Now, just I want to see if you want to plot AA comma BB, oops, and you may be covered. You can see here, it just looks completely random. I mean, it's not through here. You can draw it just equally through there or there. Okay. But now I've created the linear model, and if I sue it, I see that I get this. But if I look at summary, nah, oops. Okay, so in this case, you see I get small t values. So the probability of getting that a value of that or bigger is, so there's a 61% probability that you'd get a value of 0.05 or larger, given that the hypothesis is 0. So this is way bigger than 5%. So you're absolutely going to reject the hypothesis. You're absolutely going to accept the hypothesis that the true coefficient is not 0.05, but it's 0. And similarly, that's the intercept. And similarly, if you looked at the slope, you get a value of 0.04, you get a standard error of 0.11, the t-value is even smaller, 0.93, and there's almost a 70% chance that you'll get a value of 0.393 or larger if, in fact, the true hypothesis, the hypothesis is true, that the true value of AA coefficient is 0. So in this case, you will see, based on this, that you would, if you say the hypothesis is that the true values are 0, you're going to accept both hypotheses, and you're going to come to the conclusion that there's no relationship between A and B, which of course there isn't. And this is reinforced by the fact that the R squared is essentially 0. And the F statistic, again, is very 0.15. So again, at any 5 reasonable percentage confidence interval, you accept the hypothesis that there's no connection between AA and BB. All right. Okay, I'm asked to explain residual error and R squared. Those I will be glad to. I think we come to those slides very quickly, and I prefer to wait till I get to the slides because then I can show you in front of you what you should be seeing. So going back, so let me just finish up. As I said, the formula is in our class, and you don't have to worry much about formulas. You'll never have to do anything more than actually put a formula like y tilde x, and I'll explain more about how you do it. Residuals are, as I said, the estimate of how much our prediction of ax plus b differs from the y value, and the coefficients are a and b respectively. And as I said, I'm going to talk more about that. Maybe let me skip the heavy weather stats. That's really important, but let me skip that to go and show you these. So the residual standard error, that's the standard deviation of the residuals. The mean of the residuals is 0, sort of by the way the model is built, and the R squared is what it is. Okay, so as I said, R squared is a percentage of variance, and adjusted R squared, we won't talk about that, lowers R squared by an amount depending on how many variables, and I've discussed those. All right, so now I'm going to answer your questions. We have these yi's, which are the observed values, and then we have these hat. You see yi hat, these are your estimates. So if you have xi value, you estimate yi by yi hat is axi plus b. And so then I let epsilon I be the difference. So that's the residual. So the residual is the residual and error term mean the same thing. They are the difference between um, your actual value and your estimates. Okay. So I call SSRS for residual. You square the errors and you sum them. So that's the residual sum of squares. Okay. But each of these epsilon i's has a value, and so if I looked at the variance of that, that's the what they call the standard error. That's how much on average the epsilon i's differ. And of course, since these epsilon i's have mean zero, this is also the variance of the epsilon i's. Variance is just the standard statistical term. The variance is, you know, how much on average they differ from. So if you take this and divide by the number of observation points, that'll be your standard error. Okay. Now, the variance of the y's, if I let y bar be the mean of y, then the variance of y, which is sometimes called SS total, is just the sum of how much your yi's differ from their average value on average. And I've left out the divide bys, because what I really am interested in is we define r squared to be 1 minus SSRS over SS total. Now, here's the point. The total variance has to be greater than your error variance because that's what the least squares does. It finds your best estimate. Now, you could always estimate. One possibility is you say, for every yi, I'm just going to estimate it by the mean. And then I would have the error term would be the variance. So since I have the best estimate has to be smaller than the variance. Okay? And we will talk more, if you want, about this next week. I will go over the more math details again. But the point is the standard errors have to be less than the total variance. So this number has to be less than 1. Now think about it. If this number on top was 0, what would that mean? That would mean there are no errors, and your variance is totally explained. Everything you're seeing is totally explained by your model. You'd want that to be perfect. On the other hand, what would it mean if your best estimate was to just use the mean? That would mean that these two numbers are the same, and you don't have a very good estimate. You're just estimating every one of your data points by the same value. This is 1 and r squared is 0. So this is a measure of how bad your model is. So 1 minus it is an estimate of how good your model is. And because of what I said, these terms are positive and is always smaller than 1, so r squared is always between 0 and 1. All right. So I hope that explains a little bit better where this comes from. So maybe I'll just go over this again. Okay, we have yi is the observed values. That's the values we have. We're estimating yi's by yi hat, which is given by our formula axi plus b. And epsilon I is the residuals or the error term. At epsilon I is the residual or the error at y. So SS sub rs is the sum of these squared. That's just the variance of the errors. SS total is the variance of our observations, how much sort of diversity there is in our observations. This has to be smaller than this because I can always estimate. One estimate is to just estimate yi always by the mean, and so we know that the epsilon i's have to give you smaller numbers than that, so we always have that SSRS is less than SS total. Okay, because this is certainly an estimate. I'm saying every time I want the value of yi, I'm just going to guess the average value. That's certainly an estimate. That would correspond to a equals 0 and b equals y bar. Okay. So then r squared is given by this formula. Now, if you want to spend some time and look and stare at it, I think eventually what I just said will all make great sense. If you don't, the main takeaway is you should always remember that R squared is between 0 and 1. 1 is perfect, and it is an explanation of the percentage of what the variance you're seeing in your data that is explained by your model. So it's telling you it's a measure of between 0 and 1 of how good your model is. Okay, maybe I'm going to skip this till next week, but this is just repeating that. But the main thing is if you want more information, you can get, rather than using the summary function, you can use the structure function, and the structure function will show you everything that's in there. And so you can see there's a lot of information. Most of it you rarely will have to do, but it'll give you the coefficients. It'll also give you the residuals, so you don't have to calculate them. It'll give you the fitted values too. So if you want to know what are you actually fitting, and what are the errors, you can get this from here. So for example, if I looked at $, residuals, it's just going to print a list of all the differences between my best guess and my estimate. Okay, and again, I will talk in more detail next week when we've gotten to use it a little bit more about all the outputs, but all the outputs are all this information. And if you go here and type $LM, on the right side, you'll get, under help, the information, and it'll show you how you call it, and it'll explain what all these things are and what all these things are. Okay, so the question is, why is the degrees of freedom 98 or 99? If it's 98, I'm guessing it's in the F squared statistic. Remember, the degrees of freedom is how many free variables you have. If you have 101 observations, that's 101 degrees of freedom. But once you've calculated the mean, you're down to 100. Once you calculate the standard deviation, you're down to 99. But once you calculate the mean, and then if you calculate the x value and the intercept, you'd be down to 98 degrees of freedom, because you're using 3 quantities at that point. So depending on exactly where you are and where you're looking, the degrees of freedom can be different. If you calculate the standard deviation, you have 100 degrees of freedom up to that point. So it's just a question of how many quantities that you calculate from the raw data that you have done. So if you have the mean and you have the x-intercept and the x value and the intercept, would have 98 degrees of freedom at that point. Okay, so let me go forward. All right, I would be very remiss okay, I think we've actually done that. Okay, so all these outputs from the linear model are statistics. Now here's I'm asked, are we going to cover the concept of adjusted R squared later? And the answer is probably not. Adjusted R squared has no theoretical justification. It's just an attempt to, in an ad hoc manner, judge how much the true value of your model is degraded by adding more variables. There are much better methods that are statistically and mathematically justified. In the old, and again, in the old days, prior to good computers, you might have used adjusted R squared, because computing something like a Kachi information criteria or Bayesian information criteria, or doing cross-validation, or doing bootstrapping, you just couldn't do it. It was just impossible in practice to do it. It took too much computer time. But I mean, my own personal opinion, which you're going to have to live with, is that adjusted R squared is an artifact from the days when it was not plausible to get better measures. Okay, so it just sort of says, maybe if you like, next week I'll write it down for you. You can see what it is. But it's just a formula that adjusts R squared by a ratio related to how many variables you have. Okay. So, but the important point, and these are important to keep thinking, the hypotheses that for these standard errors, for these assumptions, are that the error terms are uncorrelated. That means if your error term is positive one time, it's just as likely to be negative the next time as positive. They have mean zero and they have constant standard deviation. That is, on average, the errors shouldn't look too different from each other. Now, this is a really important point. When you're dealing with real data, sometimes this will be nearly correct, but it's never exactly correct, and there's lots of data in the real world that doesn't obey these assumptions. So I can't prove this, and I don't know anyone how way to prove it. No one has yet disproved it to me, but my basic claim is when you deal with non-human data, astronomical observations, distributions of a chemical, in a solution, you can see essentially normal data, and these models will be exactly correct. Whenever your data deals with human behavior, whether it be how people respond to education, or how education increases their income, or how stock prices come about, you will never observe normally distributed error terms. Okay, so you also have to assume, as I said, uncorrelated, and that means there's no pattern in the error terms, and the average of the noise term is zero, and the standard deviation is constant. So in other words, you don't see times where when you look at the plot, the standard deviation, the errors are small, and then you go to areas where the error is large, and then you go to areas where it's small, and there should be no pattern to whether the errors are small or large. Only under those circumstances are the things like t-values and the probabilities that your coefficient are non-zero are correct. All right, so I just to write this down mathematically, it says that the correlation of epsilon of one error term with another is zero, and that the variances are all the same. Okay, so I've given you a long discussion explaining that you can always create the least square model, right? But the information that the linear model function prints out needs to be taken with a grain of salt, because it assumes that the residuals are the residuals or the error terms are uncorrelated or normal. So here's quiz 3. Which of the following is true? We can only compute the least square model if the residuals are uncorrelated or normal. 2, we can always compute the least square model, but the accuracy of the estimates of the coefficient depends on the properties of the residuals. And 3, the residuals are always normally distributed. So I'm going to give you a second to stare at that, and then I'm going to give you quiz 4. Okay, so some people are already replying. So the question is, which of the following is true? 1, we can only compute least squares model if the residuals are uncorrelated and normal. 2, we can always compute the least square model, but the accuracy of the estimates of the coefficients depends on the properties of the residuals, namely, are they uncorrelated and normal? Or 3, residuals are always normally distributed. All right, everyone so far, well, most people so far are getting the correct answer. I'll give you another 5 seconds. Okay, it looks like 83% for number 2 and 17% for number 3. Now we got somebody voting number 1. Okay, and this is just so important. We can always compute the linear model. We can always get estimates of the coefficient, but we do not know off the top of our heads if the residuals are uncorrelated or normal. That's a different issue. But we can always compute the least squared model. That's a matter of mathematics. So we can always compute the least square model, but the accuracy of the estimates depends on the properties of the residues. In particular, I'm just going to keep repeating myself from now to the rest of it till we're done with linear regressions. The estimates depend on that the linear model LM function, pulls out, depends on the assumption that the error terms of the residuals, same thing, are normally distributed and independent of each other. Are the residuals always normally distributed? No. We have to have some sort of check for that, and we will discuss that later on. Okay, I want to make one more quick point, and then I want to do some examples to end it. Everything I said makes sense if there's more than one explanator. That is, if we want to explain a model on more than one thing, we can do that. So, for example, suppose we want to predict the price of a stock based on the price of 5 other stocks. Or suppose we want to predict somebody's income based on their education level and their sex. Or suppose I want to compute some properties of the iris based on other of them. Can we do that? But there are a few important differences that I want to point out. The first is that if there is correlation between the different variables, the results are very unstable. Okay, so this is part of the troubleshooting, and we'll spend more time on this. But the 10,000 foot view is that if your variables are correlated, the answer you're going to get are very unstable. So I won't step through this right now, but what I've done is I've created two models. Okay, we start with the identical input and just add random noise 2 times. Okay, and so here we have the results. So you can see this is from the first time. This second time it's the same model, but just different random noise. And all I've done is I've created variables that are highly correlated. Okay, so you can see that if I took 2 estimates, I'm going to get wildly different estimates for what the models are. And all I've done in essence is change the values by very, very slight amounts. So if you have variables that are correlated, you have problems. So in practice, when you want to do this, you have to make sure your variables are not highly correlated and remove ones that are. Adding more variables will always increase R squared, but that doesn't mean the model is better or has great explanatory power. So I was asked about adjusted R squared, and without going into a formula, again, adjusting R squared for the number of variables, which is what our adjusted R squared is an attempt to take into account the fact that R squared always increases. So what I've done here is I've just taken a U and I've created W. That's 2 times the value U plus noise. And then I've created the model, and then I've created a 4th model that instead of explaining, trying to explain W against U, I use another variable, excuse me, XX, which I created previously and has nothing to do with W. U and W are clearly related. XX has no relation to either W or U. But when I look at the models, I get a 0.73 R squared for this model, which is really the right one, and I get a model of almost an R squared of 1 for the 4th model, and all I've done is I've added 10 noise variables. So this is a famous phrase is, model 4 is modeling the noise, and it's an issue. If you add too many variables, you're going to get very good R squares no matter what you add. And this is about as good an example of that as you want. I've created a perfect R squared by adding noise variables. This is some more details I'll go into next week about why and how you have to deal with correlated variables. I will give you this. You can look at this week. This is worth mentioning now, and that's there's always an issue with categorical variables. Categorical variables can only take a finite number of variables. So for example, if you had sex, you have male and female. So what's happening to the females is always, the opposite of what's happening to the males. So if you have categorical variables, if there's n categories, there's really only n minus 1 of them that are independent. Now the good news is, if you have categorical variables, you can put them in your model, and R will take care of that for you. It'll just deal with it by dropping the last class. So this is a good example. Again, without going into detail at the moment, I've just created some random variables, and I have sex, and I have female and male. And if I look at, and I've just created data, and sex is one of the variables, and I can do one of two things. If I just tell I want to create a linear model on Y on sex, you can, you can see that what it's done is it has the intercept and sex male. It doesn't deal with sex female. Okay? It knows that the sex is a categorical variable that takes two values, male and female. If it added sex female, this would it would be 100% correlation between those two variables, and because sex female is 1 minus sex male, and it would lead to, you know, results that were no good. If you want to deal with it explicitly, you have to tell it, I don't want an intercept term. This +0 means no intercept term. So I can also model Y on the variables female and male and no intercept term. And if you look, you see now I get female and male as my two variables, but I don't have an intercept because I've told it +0. I want to give you an example. Let's skip the quizzes for a second since we're running late. So one of the most famous data sets ever is the iris data set, which was initially analyzed by R.A. Fisher in the 1900s, early 1900s, and it has sepal length, sepal width, petal width, and species. There's 3 different species. So I just want to show you, so if you, let's say you want to use sepal width to predict sepal length, here's a nice ggplot. I told it that the data is iris, X is always going to be sepal width, Y is going to be sepal length, and the color is going to be species. What that means is each one of the 3 species is going to have its own color. And then I said, put all the points, I'll put in a scatter plot. And because I've specified the color as a species, we can see it's already taken the trouble. It tells me which color is each species, and each one of the points on the scatter plots is a different color. So all these purple ones are setosa, all the green ones are versicolor, and all the blue ones are virginica. And then finally I've said geom smooth, method equals LM, S equals full. So I didn't want to see the confidence intervals, but I've just said draw the least squares line for each of these 3. Because I put class color equals iris $ species here, it's going to do for any one of these things, point, geom smooth, it's going to do it separately for each one of the 3 species. So there we see, those are the 3 linear model lines for how we can fit the petal length to petal width. And we see there's a strong correlation. We can see that they are linear, but we can also see there's a lot of noise. But probably what you want is not this. What you want to see is the thing overall. And so if I said the data is iris, the aesthetics are my X is the width and my Y is the sepal length, and then I say geom point, so I'm going to give all the points, and now this is saying aesthetics, mapping aesthetics equals color. It means I've already said what the X and the Y is, but now I've said color the points, only the points, because I've done it in here. And geom method equals LM, means now create the least squares line, but do it on all the data. I haven't set it to do it separately by data. And you can see you get a very different line. Okay? Oops. Here they are side by side. Here's the 3 separate lines, which show that as sepal width increases, sepal length gets bigger too. This is absolutely clear. On the other hand, when you look at all the data, it seems to indicate that as sepal width increases, sepal length decreases. Now, hopefully you remember we had a discussion about something called Simpson's paradox, which basically said that when you clump together different groups, you could get different and very wrong answers. And this is a great example of this for this data. It shows that if you clump the different species together, because the way each species works is so different, you can see they're in different places. Once you clump them all together, you get a completely wrong idea of how width is related to length. Because what happens is these points here, all these points being down there, pulls down the least square line. Incidentally, you can also see that the fit is, god awful. But nonetheless, if you were doing a linear model, you would say, well, no, as sepal width increases, sepal length decreases. When the correct answer is no, as sepal width increases, sepal length also increases, but it does so at such different, levels for different species that when you clump them all together, the fact that you have all these points down here pushes the line away. Now, incidentally, this getting these side by sides, you need an extra package, Grid Extra. And what you do, remember I said you can put all your data and just say my ggplot is this. So here I create plot 1, which is this thing on the left. See, here's the color up here. And plot 2 is the thing on the right. You can see I only color the species. So these things have, the points are different colors, but there's only one line. And so then I say grid arrange. I have plot 1, I know what that is, and I have plot 2, and I say end columns 2, it means put these in 2 columns. And there we have it. And so that's how you get side-by-side graphs, or it's a way to get side-by-side graphs in ggplot. So let me just show you. So recall, we have 1, 2, 3, 4, 5 variables. These first 4 are numbers. This 5th is a categorical variable. Right? There are 3 different species. So species takes 1 of 3 variables. It's a categorical variable. Now here's something really nice. I want to make a linear model. I want to predict sepal length against all the other variables. So the tilde signs this formula. The dot means use everything else. Okay? And my data is iris. So once I've told it my data is iris, it knows what sepal length is, and it can do it. And so here's my summary. So it gives me an intercept. Now look, remember there were 3 species, and it only gives versicolor and virginica. I don't remember the third one off the top of my head, though we can. There's setosa, versicolor, and virginica. But it's not going to use it because it's a categorical variable with 3 variables, so it should only use 2 of them. But here it does. It gives you the estimates. And you can see virginica has negative estimates. And what does it say? It says the intercept, the sepal width, and the petal length are all the probability of getting values that large, given the hypothesis that the true value is 0, they're all essentially 0. So it says these 3 are very likely. Now the worst one is petal width. It says the probability of getting an estimate for the petal width coefficient of minus 0.3, given that the hypothesis that the true value is 0 is -2, is a probability of 3.8. So you would still include this in the model in all probability, and these 2 are slightly better. But if you wanted to throw out a variable off the top of your head, this is the one, top of your head, this is the one that appears less significant. Excuse me. Now here, I just want to make a model. I want sepal length in terms of petal length and petal width, and I don't want a constant term. I just want to do it from those 2. So I say sepal.length tilde petal.length plus petal.width plus 0, and of course I still give it the data as iris. That will create a model with just 2 coefficients for petal length and petal width, and we see this works. Okay. If I want to do this, so sometimes you're going to see people see attach. Whenever you write an attach statement, you should always write a detach statement at the same time to make sure you don't forget. And attaching iris means that all the variables in the iris data set are now there. So I can just identify things. Now I just don't have to say the data is iris because sepal.length and species are now variables in my environment. Okay, if you have a large number of variables, this may be useful. But again, you can see it just, again, because the species is a categorical variable that takes 3 values, it gives you just 2 of them, and the intercept really stands as a proxy for the third. So, okay, so still to be done, as I said, this is a 2-week endeavor, is I want to go over the math a little bit more next week, because I think that this, you need some time to let this sink in. I will discuss a little bit about ANOVA, which is analysis of variance. And I wrote something here. If you like the chi-squared lecture, you're going to really like ANOVA. In some sense, ANOVA is chi-squared for continuous variables. But all I would say today is that if you ran an ANOVA, what it's really doing is telling you the likelihood. When you run ANOVA on a linear model, it's giving you the likelihood. It's telling you about the likelihood that some of the variables should be in the model, and it's helping you to fit the model if you don't want to have all the variables. We're going to discuss diagnostic plots, in particular QQ plots, which are ways of looking at the data and sort of getting an idea of how bad the errors are, how much they do differ from normal. I want to talk a little bit about polynomial regressions and other variable transformations, because in the real world, it's rarely the case that you're given the right variables. You usually do have to spend some time thinking about making various transformations and understanding interaction terms. And polynomial regressions are a great way to understand interaction terms. And then I want to do more examples. And so that's what's left to be done, and more examples will be a lot of it. And maybe even if I have a chance, either next week or the week after, we'll start talking about how you use the dplyr package to subset your data sets. Yeah, I have a couple of questions. I'd like to answer them, and then I'll say goodbye. Did not get the issue with when one of the independent variables is categorical. All right, so typically these things are complicated, but the point is what R does with a categorical variable is it creates something called dummy variables. So for example, if your variable is sex, it's male or female, actually in the United States of America, and under current conditions that would not quite fly. There'd probably be a good half dozen different values for sex, but that's okay. So really, let's just keep it simple and say sex can be the male or female. So it would create a variable called male, and that would take the value 1 whenever your categorical variable took the value male, and 0 otherwise. It would create another variable called female that took the value 1 whenever you had female, and 0 otherwise. Now, if you think about it, since you can either be male or female, once you know, if I know whether you're a male or not, I know whether or not you're a female. So those two variables are 100% correlated. They both take the value 0, 1. They're called dummy variables. So if you include both of them, you're going to have a correlated variables. So you only include one. The same thing is true. I mean, in the case of species, you have the iris can be one of 3 species. So I create a variable called species 1, which takes the value 1 when the observation is of species 1 and it's 0 otherwise. I create a variable called species 2, okay, which takes the value 1 when the observation is of a species 2 and it takes the value 0 otherwise. But I don't have to create the variable species 3, because if it's not species 1 and it's not species 2, then it is species 3. So in other words, when is species 3 going to be 1? It's when species 0 and species 2 are 0. So this third variable, species 3, is automatically 100% correlated with the first two. So there's no need to include it in the regression. and R will automatically do that for you. So if you go back, here, I want to do sepal length as a function of species. Instead of having the third variable, it tells you for any, if you give it, and by the way, what this means is if you tell it, you know, predict what it is. So in other words, if you want to do it, this formula will do it. What is it going to say? Well, it's going to say, suppose you want to know what's the value for species 3. Well, that means species 1 and this species and this species, Versico and Virginica, are 0. So it's always going to say the estimate for species 3 is 5.06. Okay, which is, I guarantee you, the mean value of the sepal length for the third species, which I think is Septica, but I don't remember. So that's how it works. All right, I will have the midterm done by Monday or so, and I will discuss with Manish and Stephen exactly how it will be done. I will create the midterm. I will allude to them the exact details, but I will also create a document explaining exactly what will be covered. I'm asked to show in question 6, can you show how we replicate bootstrapping in R? Is it done using replicate and generating multiple sample means? All right, I will show you a sample, and I will again put out in a couple of days. I'll just do the homework and show you how you do it. It's not bootstrapping. You could do it with replicate, but there's really, you don't need to, and I don't suggest using replicate. I mean, in some sense, so let's say you want to bootstrap. So in the sample, you wanted to, get, the estimates of the average weather. You created samples. Now, what you could do is replicate, the function of taking a sample of size 100. But if you just use replicate in a straightforward way, what does that mean? I take a sample of size 500. I replicate it 1,000 times. What have I done? I've created 1,000 copies of the exact same sample. So if you replicate, sort of a functional version, you say replicate, create a sample, you could do it. But it's the more I think about it, I mean, I go from you could but to you really shouldn't. So that's really the for next loop. I mean, the point is, whether you bootstrap, is you create a new sample. You do this 500 times. So you're replicating the procedure. That's what the for next loop is doing. But you need to be careful that while you replicate the procedure, you don't replicate the exact same sample. And the best way to do that is not to use replicate at all, but rather to use the for next loop, and for 500,000, whatever number of times you want, sample. Okay, so the procedure would be, let's say I want to replicate 1,000 times a sample size 500. So for I equals 1 to 1,000, that means 1,000 times I'm going to do this loop. And in the ith loop, what am I going to do? I'm going to create a sample of size 500 the ith time, and then I'm going to take the mean of that sample, and then I'm going to store that in the ith bin of someplace. Any other questions? All right. Okay, so I'm going to stop recording.